pressure of hydrogen gas. Relative molar mass is given 2. In a container is 2 atmosphere. If helium gas, relative atomic mass 4, is added to the container so that the pressure in the container becomes 3 atmospheres. The ratio mass of hydrogen divided by mass of helium in the container is. Assume that the temperature remains constant. We know that when using PV equals nRT, we can use number of moles, mass divided by molar mass, RT. Now we can get these are constant, V and RT constant, pressure directly proportional to mass divided by molar mass. Then we can get for the initial situation, pressure is 2 atmospheres. I will not convert the unit. 2 directly proportional to initial mass, hydrogen mass, divided by molar mass of hydrogen 2. First equation. Then I will consider increasement of pressure. Final pressure is given as 3 atmospheres. Therefore, increasement of pressure 1 atmosphere. It is directly proportional to mass of helium divided by molar mass of helium is 4. It is the second equation. Then we can divide both the equations. We have to find the hydrogen ratio between hydrogen mass and helium mass. Then I will divide first equation and second equation. We can get 2 divided by 1, 2 equals to mass of hydrogen divided by 2 multiplied by reciprocal of this one, 4 divided by mass of helium. 2 divided by 2, 1, 2. Then we can cancel out 2 and 2. Hydrogen mass divided by helium mass ratio is 1. Then we can get first answer is the correct answer. The average kinetic energy of a certain amount of ideal gas, K, when this gas is allowed to expand so that its volume doubles, the pressure of the gas is found to drop by factor of 3. The new average kinetic energy of gas. We know that average kinetic energy of a gas is directly proportional to temperature. Then we have to consider change of temperature by the process. But they have given when this gas is allowed to expand so that its volume doubles, pressure of gas found to be dropped by factor of 3. Then we know that PV over T is constant. Volume doubles, then volume is 2 times, pressure 1 over 3 times. Then we can use this equation for the given 2 situations. P1 V1 divided by T1 equals P2 V2 divided by T2. For the initial situation, pressure P, volume V, temperature T. For the final situation, pressure 1/3 of initial value, T over 3, volume doubled 2V. We have to find temperature. I will consider temperature as T dash. Then we can cancel out V and V, P and P. Then T dash equals to 2 over 3T. Then initial average kinetic energy is K. It is directly proportional to initial temperature. If the final kinetic energy K dash, it is directly proportional to this value, 2/3T. Then we can divide both the equations. K divided by K dash equals T divided by 2T/3. Then we can cancel out T and T. We have to find K dash value. K dash is 2/3K. Then correct answer is 2. A hot air balloon of constant volume contains air at 100 degrees Celsius. See the figure. When the temperature of air inside the balloon is raised by 2 degrees Celsius, the fraction of air which escapes is approximately equal to, they have given, assume that the air behaves as an ideal gas and the pressure inside the balloon remains constant. For the air balloon, volume is constant. Volume is not changing. And they have given pressure remains constant. Then PV equals nRT, PV constant, R constant. Then NT product for both situations should be constant. Then I will consider number of moles into initial temperature should be equal to number of moles into final temperature. Initial number of moles in one, initial temperature is 100 degrees. We have to substitute in Kelvin. 100 plus 273, 373 Kelvin. Final number of moles into multiplied by final temperature 375. Then we can get the ratio between initial number of moles and final number of moles. I will subject final number of moles into, it is 373/375 in 1. Now we have to find the fraction of air escape is approximately. Then escape air, number of escape air moles, we can subtract N1 and N2. N1 minus N2 value is this one, 373/375 N1. Then answer is 2/375 N1. When getting the ratio, we have to divide this value by initial number of moles. When dividing by initial number of moles, we can remove this one. Then answer is, ratio is 2/375. Answer is 2. When the pressure of a given mass of an ideal gas is doubled, while the volume is kept constant, the average translational kinetic energy of gas molecules will PV/T constant. When pressure is doubled, they have given volume constant. Then temperature also should be doubled. Therefore, translational kinetic energy should be doubled because of kinetic energy directly proportional to temperature. When temperature is doubled, kinetic energy should be doubled. According to the Boltzmann law, we know that according to Boltzmann law, kinetic energy can be represented 3/2 times kT. K is Boltzmann constant. Then kinetic energy directly proportional to temperature. Then answer is 3. Two bulbs X and Y of volume 2V and V and 2V immersed in a constant temperature bath containing two ideal gases having relative molar masses 2 and 28 respectively. Two bulbs are connected by narrow tube and The gases are separated by a small pellet of mercury. See as shown in the diagram. The ratio mass of gas in X divided by mass of gas in Y. When considering the system equilibrium, of given mercury thread, there is the same pressure in both bulbs. According to PV equals nRT, we can use number of moles mass divided by molar mass RT. I will subject P MRT over MV. Then pressure should be equal for the equilibrium of mercury thread. Then we can write for the gas A, gas in bulb X, we have to find mass of gas X, Mx, are constant, temperature constant because of there are two bulbs in same water bath maintaining a constant temperature. Divided by molar mass of gas X is 2, volume is 2V. Volume is V. Then we can equal to the pressure of gas in second bulb, mass of Y, R T divided by molar mass 28 into volume is 2V. Then we can cancel out 2 and 2, V and V, RT, Mx divided by My is 1 over 28. Then answer should be 1. A closed cylinder contains the gas mixture of hydrogen, nitrogen and oxygen at constant temperature. The pressure inside the cylinder increases most of capital M gas. Grams of, we have to find the gas type. We know that pressure is directly proportional to number of moles. Number of moles means mass divided by molar mass. Then using this relationship, we can get that when the molar mass is small, there is a large number of moles. Then we can identify the smallest molar mass for hydrogen. Therefore, maximum number of moles is for hydrogen. Therefore, maximum pressure maintained by a constant mass of hydrogen. Then answer should be 1 for the pressure. Of the following graphs best represent the variation of volume V of fixed mass of an ideal gas at constant pressure with its absolute temperature. PV divided by T is constant. Then we can subject volume V equals kT divided by pressure. Now there is a constant pressure. These two values are constant values. Then volume directly proportional to absolute temperature. Then we can obtain a graph like this. Answer should be 4. Number 8. A tube of length L closed at one end is slowly lowered vertically into a liquid bath so that the open end first dips in the liquid. The air inside the tube does not escape if the length of air column inside the tube becomes L over 2, then the liquid meniscus inside the tube is at a depth h from the liquid surface of the bath. The atmospheric pressure expressed in terms of height of liquid column. We can get for the initial situation, pressure is atmospheric pressure. I will consider it as P0. After immersing this one in corresponding liquid, volume is half of this one because of initial length L. Now length of air column is L over 2. They have given this meniscus is at a depth of capital H. Then we can get pressure for this one. Atmospheric pressure plus capital H by using corresponding liquid height. We know that when using liquid height, we can use liquid height to indicate pressure, like mercury millimeters or mercury centimeter. Then pressure at this place is atmospheric pressure plus H in liquid height units. Then we can use PV equals constant, P1 V1 equals P2 V2. Initial pressure, atmospheric pressure, volume, cross-sectional area into initial length L should be equals to final pressure, this one, P0 plus H. Volume should be A L over 2. We can cancel out A and A. Then we have to find P0. 2 times P0, 2 P0, L is cancelling, equals P0 plus H. Now P0 equals H. Then answer is 2. And the ideal gas is kept inside the rigid container. The another ideal gas is added to the container. The variation of pressure P inside the container with the absolute temperature T before adding the second gas A and after adding the second gas B are best represented by. We know that when increasing number of moles in a container, pressure is increases. Pressure is increasing and we know that pressure is directly proportional to absolute temperature. Therefore, graph should be past the origin and after adding gas, graph should be this one, and before adding gas should be this one. Then answer is 2. An ideal gas of volume 300 cubic centimeters at pressure 1 atmosphere and temperature 27 degrees is compressed to 5 atmospheres. Then heated to 127 degrees constant pressure. The new volume of gas would be, there is a constant pressure for the final situation when increasing temperature. But when considering initial and final situation, P, V, T, all values are changing. Then we can use P1 V1 over T1 equals P2 V2 over T2. Pressure for the initial situation 1 atmosphere, volume 300 cubic centimeters, initial temperature 27 degrees, 300 Kelvin. It should be equals to final pressure 5 atmospheres. We have to find the final volume. Temperature 127 degrees, it means 400 Kelvin. Then we have to simplify. We can get volume 400 divided by 5, 80 cubic centimeters. Then answer should be 3.